continue kind of our story of atomic theory. So before we dealt, let's take out actually our notes from last day and just recap those old dead guys that we talked about before. So our notes from last day, we talked about Dalton. He was the billiard ball model, okay? And then we talked about J.J. Thomson, and he discovered the electron using the cathode ray and made the plum pudding model. Then, okay, Rutherford made the planetary nuclear model, okay, with his experimentations on gold foil. Now, your quiz tomorrow, you need to know all those names and their main experiments and their models. Okay, so that's stuff that we've done since Science 10, so it shouldn't be too overwhelming, but you need to know those names and the models, okay? So, Dalton, what model? Billiard ball, okay? Maddie, what's Thomson's model? The cookie or plum pudding? What did he use to discover it, Hayden? Or what experiment was he doing, Thomson? Cathode rays. He was studying it with cathode rays. That's Rutherford. Rutherford did gold foil. Cathode rays was J.J. Thomson. Okay? So Rutherford did the gold foil experiments. Okay? And he made the planetary model. Now, there's one thing that we didn't put in our notes that will be on your quiz tomorrow. I alluded to it. So in your notes at the bottom with Rutherford, okay? So we looked at Rutherford and a problem that was about his model. Okay, so the main problem with his model was that if the electrons are orbiting, okay, we said if they're orbiting, then they are in a circular orbit, which means they have centripetal acceleration. So the problem here, we had it in our notes, but an accelerating charged particle will emit EMR. And if the electron is emitting energy, it will lose kinetic energy and spiral into the nucleus. Electrons will emit EMR as if it moves in a circular path and loses energy. So the guy who noticed that and said, hey, that's a problem, was Maxwell. Okay? So Maxwell was the guy who pointed out those problems with Rutherford's model. Okay, so kind of at the bottom where we're explaining the issues with Rutherford's, the guy who identified these issues is Maxwell. So I'll just state something for you so you can just listen. Rutherford's planetary model of the atom had to be revised because of Maxwell's electromagnetic radiation. Because Maxwell, like we studied him when we did EMR. When we were looking at just at EMR, that's what Maxwell said. He claimed, okay, about EMR. So if Maxwell's EMR statements are true, then this needs to be revised. So Maxwell's theory claimed that accelerating charges release EMR, which is the answer to your question for your quiz. Okay? So that's where we are at in our story, is that, okay, well, Rutherford made some developments, but there's some problems with it. Like this, the planetary model is not the most accurate model. Do you see that? So in our last lesson, it wasn't that Rutherford's model was like, okay, now we got it figured out. It was like, okay, that's what Rutherford thought. But we identified an issue. So now this is where we're going to end, or we're going to pick up with our story, okay, of the atomic theory. So we've heard all these guys since Science 10 about it, but now since you know more about the actual physics and what they were actually experimenting on, you can understand in a deeper way what they discovered. So here's where our story is set. It's set in 1912. I put that in there for Maddie because she's always curious when this happened. Okay? Niels Bohr. So now we're dealing with Niels Bohr. He studied for a few months at Rutherford's lab. Okay, so now we hear that new name, Bohr. Both Bohr and Rutherford recognized a critical flaw of the planetary model of the atom. Experiments had shown that accelerative charges emit EMR waves as predicted by J.C. Maxwell using a mathematical model. Electrons orbiting a nucleus are constantly accelerating, changing direction due to circular motions, so they should emit EMR. As a result, the electrons in an atom should spiral into the nucleus within a few microseconds. But empirical evidence indicates that electrons don't do that. So there must be something else. So, this is exciting. In order to explain both of these observations, that electrons must have a way of emitting EMR and not spiral into the nucleus. So what kind of model can explain that? So we need electrons kind of like orbiting the nucleus, but they can't be spiraling into the nucleus. So Bohr, he's like, I'm going to go visit my buddy, Hansen, who told him about his studies in Germany regarding spectroscopy. Okay? Hans said that the wavelengths of the light in the spectrum of hydrogen have a mathematical pattern. But nobody understood the pattern. So he was just studying spectroscopy, which is like studying how different things will either absorb light. So when we think about black, it absorbs all wavelengths of light, right? Okay, so it's just, that's what spectroscopy is, like looking at the spectrum of something. So this gave Bohr an idea. And this is where we start going into the new, another model of atoms, is with Bohr's methods. So Bohr studied the spectra that was produced from a hydrogen atom. Spectra. Which helped him develop his theory of the atom to overcome Rutherford's shortcomings. From previous scientists, Bohr knew that if you shone light through a prism or a diffraction grating, light would be dispersed. This was from our unit C, right? Looking at the refraction and dispersion is two different ways. Or refraction and diffraction is two different ways of dispersion. The rainbow pattern that is produced, that means when one color continues into the next, is called a continuous spectrum. So when you looked at a rainbow or even looking at the prism, it's like each kind of goes into the next one. You know, like there's not a definitive line where it's like, okay, this is yellow and then this is orange. It kind of molds into each other. Okay. So here we can see, don't flip the pages. It's really important that we understand this. So this was like kind of say the first part of his experiment. So here, this is going to be the manipulated variable, okay? What he shines the light through. So let's just even identify that. So we're going to look at different examples of when this is the manipulated variable, okay? What we see on the other end is the responding variable. So for this one, we're told that it is a hot source object emitting white light. Okay, so a hot source object, which is gas. Okay, he uses gases to do this. So the next little thing is about that. So now you can hear me. So this is explaining what we just looked at. Bohr decided to pass white light from a glowing object through an unexcited gas. Gas that is cooled and has very little energy first, and then through a prism or a grating. Bohr observed that the same continuous spectra was produced, but it had dark lines appearing in the spectrum. These dark bands meant that those particular photons with that specific frequency and wavelength were missing. Very, very important. So here, in this next picture, you can see that he's shining light through. So here's the light coming through, but now it goes through a cold and transparent cloud of gas absorbing some colors. Okay, so it's still the same light coming through, but now it goes through a different gas. Okay, then it goes through a slit and then a prism. So now what is observed, so this was the manipulated variable, what we changed here. And this is the responding. So what he's saying, what our observation here is that now look, there's actual black strips in the spectrum that used to be all continuous. Okay? So now, if we look at this, the only difference between these two, there was a prism in the first one, right? So the only difference is that there's this gas here, okay? So why is this gas causing the result of dark bands? What is happening?